Standard geographic mapping shows you where a field is. In precision agriculture, that map functions as an active command center for your entire operation. Our goal is to take a digital property boundary and walk it through a complete system. By the end of this workflow, we will produce a fully AI-analyzed prescription file, generated completely offline and ready to plug directly into your tractor. Before we start routing data, check your environment. This plugin requires QGIS version 4.0 or higher to run. Here, you can see we are running version 1.0.4 of the Intelligenc's Agricultural Intelligence plugin on a compatible build. The interactive tour outlines our roadmap. We will move through 5 specific capability layers, bringing in external WFS data, fusing it with agricultural intelligence, running the AI offline, exporting the prescription to equipment, and finally, using an AI agent to drive the process. Bridging this gap is critical. When spatial data requires round trips to distant cloud servers or manual formatting by a technician, planting windows get missed. Keeping the AI workflow localized and immediate prevents those costly delays at the farm level. Step 1 is establishing our geographic foundation. Because the tools we are using are geography agnostic, you can apply this logic to a parcel in Nebraska just as easily as a field in the Netherlands. We pull this initial boundary data using the Web Feature Service, or WFS. You navigate to the WFS connection dialog and link a compliant government source, like the USDA NRCS Soil Data Mart in the US or the PDOK BRP for Dutch crop parcels. Once connected, bring those layers into your project. You must verify that the raw, unenriched geometric polygons physically render on your QGIS canvas before moving forward. With the map populated, select the specific field you want to analyze. Highlighting the exact polygon is an absolute necessity. The Intelligenc tools require a defined spatial boundary to pull accurate metrics. This initial import solves a strict geometric problem. We have to anchor our project to verified real-world coordinates first, ensuring any environmental intelligence we attach later is bound to the correct physical location. Now we fuse the Intelligenc. Open the Soil tab in the Leaf Engines panel. Use the County Lookup search bar to find your area, then click Get Soil Data to pull the USDA composition metrics for your selected polygon. We can stack more context immediately. By switching to the Water tab, clicking Get Water Quality queries the EPA database and overlays those territorial metrics onto the exact same footprint. Next, move to the Carbon tab. Here, you input field specifics. By setting the organic matter level, like this 3.00% value, the system can calculate estimated carbon credits for the designated acreage. To evaluate runoff and biodiversity, go to the Impact tab. A single click on Run Environmental Assessment processes those regional risks for your selected county. Finally, open the Crops tab. You can leave the crop type blank or specify something like corn, then hit Get Recommendations to prompt the AI to synthesize all this accumulated data into actionable planting advice. As you run these queries, the results write directly back into the layer's attribute table. Values like LEPH and LE risk score become new data columns, permanently attaching the Intelligenc to the geometry. By forcing separate soil, water, and climate databases to overlap on one strict boundary, we expose intersecting operational risks, like high runoff potential in low pH zones, that isolated spreadsheets hide. We have a fully enriched map, but cloud-dependent agtech fails at the boundary of a Wi-Fi network. Out in remote agricultural zones, cellular signal drops out entirely. Enable on-device mode in Layer 3 to activate a local GEMMA model. It generates responses in 2 to 5 seconds without network access. Prepare this before leaving the office. The first launch requires a 600 megabyte download to cache the model forever. With the model cached, you can take your laptop miles from the nearest cell tower, run your field queries, and watch the AI process complex multivariable recommendations instantly, directly from the tailgate. Severing the network connection solves 2 distinct problems. It guarantees operational continuity for farmers working in dead zones, and it provides strict data privacy for enterprise clients who require workflows where no data ever leaves the local hardware. All of this digital analysis is useless if the tractor sitting in the field cannot physically interpret the coordinates. To translate our map into hardware instructions, open the Export dialog. Generate your prescription in standard formats, like the ISOBUS XML format for John Deere monitors. For older equipment, select the zoned shapefile option, readable by legacy controllers. The plugin executes the conversion and writes the localized prescription map directly to your local disk, ready to be dragged onto a portable USB drive. Relying on the strict ISOBUS standard for this handoff removes the risk of manual data entry. It ensures the variable rate seed and fertilizer instructions hit the hardware exactly as the AI modeled them. This is the physical culmination of the entire process. You carry the intelligence out of the digital environment and load it straight into the machinery. In about 10 minutes, you have completed the full loop. You pulled raw geometry, fused it with soil and water data, ran an offline AI analysis, and formatted the output for a tractor display. Your next step is to drag your generated files into a virtual display environment to verify the mapping. For deploying this architecture across an entire fleet, reach out to the partnership team to discuss enterprise scaling. By taking a simple property boundary, enriching it entirely offline, and bridging it straight to hardware, QGIS functions as a secure, end-to-end command center. It is the connective tissue between digital intelligence and physical field execution.